Supplemental math videos from Circle Christian School.
Circles and parabolas. It's too bad that poor Hypatia had to suffer such a tragic death. Who knows what she may have been able to accomplish. Some records attribute the hydroscopium to Hypatia. It was a clock fashioned of water-driven gears, most likely from a hydrometer.
In this section, we'll be talking about a family of geometric figures called conic sections, and they are so named because of their relationship to the cone. Cone, conic, that's that relationship. Now, the way that they emerge is by taking a cone and its reflection and looking at the cross-section of this figure with a plane. Now, you can see some figures drawn in your textbook that illustrate the situation very well. But imagine a plane just cutting through the cone like this. Then what we would have is, we would have a circle. And if the plane were kind of twisted a little bit like this, then the figure would end up being an ellipse. Now, the figures that are in this group of, this family of geometric figures, these conic sections, or simply conics, are the circle, parabola, ellipse, and hyperbola. All of the conic sections are defined in terms of distance. Let's start with the circle. Now, I mentioned that definitions of these figures have to do with distance. So let's begin with the idea that the circle is just all the points in a plane that are the same distance from a center point. All right, so that defines the points that are on this circle. Our goal here is to develop an equation that will allow us to place points onto a graph that form the circle. All right, so let's see. Suppose we position the circle so that its center is at the origin. So that means that the coordinate system would be something like this, y-axis, and then x-axis. All right, and let's say, just for discussion purposes, that the radius of the circle is 4. Now, we want to develop an equation related to this circle. And to do that, it might make some sense that we're going to start with the distance formula. You know, we talked about a formula to calculate distance between any two points. Well, here we're defining circle in terms of distance. Might make some sense that we use the distance formula to do that. The coordinates of this point, the origin, simply 0, 0. The coordinates of this point we can think of as being sort of a variable x-y pair, because it's a little different for each of the points that lie on the circle. Now, consider the distance formula. Here's the distance formula from before. And let's just fill in the information that we know from our figure here. The distance that we're talking about is this radius of the circle. The distance from the center, you see, is what we're talking about here. That distance is 4. And then let's see, a difference in x components. Well, I have the difference between x and 0. Now, I'm just going to use this x, this variable x, first in our formula. So it'll be x minus 0. So x minus 0 squared, and a similar idea for the difference in y components, y minus 0 squared. Now the zeros, of course, go out, so we have x squared plus y squared. If I square on both sides, I'll clear the radical. So I'll have 16 is equal to x squared plus y squared. Now I can swap these around if I want to. A lot of times when we're talking about the equation of a circle, the x squared and y squared are written on the left side of the equal sign. Now 16 can be written as 4 squared in order to emphasize the value for the radius. So when a circle is positioned with its center at the origin, the equation related to that circle is x squared plus y squared is equal to r squared. Now, with that information, we can find an equation of the circle with center at the origin and radius 7. It's a pretty easy proposition, isn't it? After all, we know generally that x squared plus y squared equals r squared. And if we're given the radius of 7, it's x squared plus y squared equals 7 squared. And we would probably write this as x squared plus y squared equals 49. Suppose the radius is to be 5/4. we proceed the same way. We start with x squared plus y squared is r squared, but in this circumstance the r is 5/4. So we would have x squared plus y squared equals 5/4 squared. Now we have to be a little careful in cleaning this up. When we square here, we're going to get, I'll just take it over to the right a little bit, this is 25/16. And we would probably not leave our equation like this, as x squared plus y squared equals 25/16. We might run through and multiply by 16. So we could write this then as 16x squared plus 16y squared. And when we multiply by 16 over here, the 16s would cancel, leaving 25. So here is an equation of a circle whose radius is 5/4 and whose center is at the origin. Suppose we want to write an equation of a circle which passes through the point 0,5. Well, let's understand what circle that we're looking to write an equation of. We've got a circle now that has a center at the origin, and it passes through the point, it passes through the point 0,5. So if I have a coordinate plane here and I identify the point 0,5, circle goes through this point. And if this is the center of the circle, then the circle looks kind of like this. By the way, the circle is one of the most difficult figures to draw well freehand. And I got kind of lucky on that one. Okay, so now we understand that to build the equation, we start with the idea x squared plus y squared equals r squared. What do we know about the radius? Well, gee, if this is the center and that's a point on the circle, then the radius is just this distance, you see, and it's 5. So this is x squared plus y squared is 5 squared, or we could write this as 25. All right, pretty simple idea. Now, what if we want to write the equation of the circle whose center is at the origin and which passes through the point -1, -4? So let's see, -1, -4. Goes through this point. So here's the center, and here's a point on the circle. Wow. So the circle then looks like, I guess I'm going to take a shot at this, looks something like that. All right, now, in order to fill our information in the equation, we need the radius. That is, we need this distance. Well, we don't have that. We can certainly find that distance, though, by considering a couple of points like 0, 0 and the point -1, -4. You see, we could use the distance formula and pop this information in and find the length of the radius. There's another way to proceed, though, and I kind of like this one. Suppose we start with the idea that we're building an equation, x squared plus y squared equals r squared. Now, remember the relationship between equations and their graphs? That every point on the graph associated with an equation has coordinates, and those coordinates make the equation true. So we could use that information and pop the information about this point being on the circle to generate information about the radius. Here's what I mean. We have a point on the circle, -1, -4. So we replace x with -1 and y with -4, and we can actually solve this equation for r. Well, let's see. -1 squared, that's 1. -4 squared is 16. So 17 then is r squared. You know, we really don't need the value of r. We're actually looking for r squared, aren't we? So if r squared is 17, then we can use this. Let's see, let's just slide over x squared plus y squared equals r squared. We just found r squared to be 17. So here then is the equation of the circle that goes through this point and whose center is at the origin. Now, if we wanted to find the radius, if we actually needed to find the radius, it would be the square root of 17. Now let's consider the situation where the center of the circle is not at the origin. We want to develop the equation of such a circle. Consider this circle. We have a circle whose center is at 2, 3 and whose radius is 5. Now, I could observe the radius just by identifying the center and counting over horizontally or vertically to the edge of the circle to establish that distance, but at any rate, it's 5. Now, we'd like to write an equation for this circle. We would start the same way that we did before. And by the way, I'm going through this routine of discussing how the equation of the circle sort of evolves or comes about from the distance formula, because I'm hopeful that if you get in a jam in the future and you forget the equation of such circles, that you'll remember the little discussion. Okay, at any rate, we start with the idea of distance, the distance formula. Now, the distance we're talking about here is the distance from the center of the circle to the outside edge. So that distance is 5. Now, if we're talking about a difference in x components, look at what we mean here. This is a general xy pair. You see, the coordinates of any old point on the edge of the circle is an xy pair. So that's kind of a variable x and y. Here we have the center established at 2 and 3. So it's the distance from this specific point to any general point on the circle. And that's how we're generating our information for the distance formula. So when we talk about a difference in x components, we're going to take x minus 2. And a difference in y's, y minus 3. So x minus 2 squared, y minus 3 squared. Now, squaring on both sides will clear the radical from the right side. And now we have this. Now, generally, we would write this information on the left side. So I'm just swapping sides on the equation. Now, here's the information from the circle that we've drawn right here. Notice that the 2 and the 3 are the coordinates of the center point. And notice that it's the 5 that's squared and 5 is the radius. So if we kind of generalize the situation, the formula for a circle whose center is not at the origin turns out to be this, where HK is the center and the radius is R. Now, I want you to notice before we go to the next problem that H and K are numbers that follow minus signs. Now, that is really important because we have to decide what we're going to do if they don't follow minus signs, as is the case up here. Let's have a look. We have x plus 4 squared, and over here y minus 1. What about the coordinates of the center? Well, it turns out that we can rewrite this and force a number to follow a minus sign here. That is, we can think of this as x minus negative 4 squared, you see. And now the number that follows a minus sign is negative 4. And here the number that follows a minus sign is 1. So the coordinates of the center would be negative 4, 1. All right, so that's the center. And the radius is found in here. The number squared to give 9 is 3. So the radius is 3. So let's see. We have negative 4, 1. Here's the center. And the radius is 3. Well, okay, from this point I can just count off 3 in all directions. 1, 2, 3. Up 1, 2, 3, to the left 1, 2, 3, down 1, 2, 3, and now I have enough points to where I can draw the circle. At least I think I can. All right, that's easy enough. Just remember that H and K are numbers that follow minus signs. Suppose we want to identify the radius and the center point for the graph associated with this equation. Wow. The equation is not in the form where we can just easily identify an H and a K. This is a more general kind of form. Now remember, we talked about forms of equations and their graphs. A standard form is a form which gives information about the graph. A general form is just a sort of an expansion of that idea. Now, the equation that we developed just a moment ago is a standard form. Well, this is a general form. We want to go from this general form to the standard form in order to be able to construct the graph. All right, here's what we do. Now, we want, remember in that standard form, we have x minus something squared. We have a binomial squared involving x. So we'll rearrange our terms so that the terms involving x will be next to one another. Like that. And now I'm going to skip a little space here, and I'll tell you why in a minute. And I'll write y squared minus 6y. I want the terms involving y next to one another. And I'll skip a little space, and I'm going to, at the same time, clear the existing constant. All right, so I'll subtract 1 on both sides, giving me negative 1 on the right. Now, here's how I'm thinking about the problem. I'm thinking about this as a pair, and then plus this business, and I'm thinking about this as a pair. Now, I'm leaving a bit of space in here because I'm going to go through the process of completing the square. Remember, we did that at one time to solve quadratic equations, but we're completing the square for another purpose here. We are completing the trinomial square in order to factor it into a binomial squared. Okay, here's how the routine goes. Remember, it's half of this, then square it. Half of 2 is 1. 1 squared is 1, so we're going to add 1 in here. But if we add 1 in here, we're adding 1 to this side of the equation. So we'd better march over to the other side and add 1 to maintain the balance of the equation. Similar idea here with the y business. Half of negative 6 is negative 3, and negative 3 all squared is 9. So we're going to add 9 in here, but if we add 9 on this side of the equation, we need to add 9 over here. All right, back over here. The factorization is relatively easy. This becomes x plus 1 squared, and this becomes y minus 3 squared. Now remember, the trick to identify the factorization is to identify what we squared to give 9. We squared half of negative 6. We squared negative 3. So that's why the negative 3 is here, and that's the easy way to identify it. Okay, so that's what we get over here. On the right, we have the 1's going out, and we have simply 9 left on the right side. Well, now we can identify the center of our circle and the radius. The center is at HK, and H and K follow minus signs. Now, this doesn't follow a minus sign. This 1 doesn't follow a minus sign, so we have to imagine x minus negative 1. So negative 1 is the x-coordinate for the center, and the y-coordinate is 3. Now notice 3 follows the minus sign. So the center is at negative 1, 3, and the radius is 3. Let's construct the graph right quick. Let's see, the center at negative 1, 3. Let's slide over here. Negative 1, 3. A radius of 3 means we go out in all directions 3 units. And construct the graph. Okay, let's talk about parabola. Now, you know we've talked about parabola in the past, and the parabola was simply the graph of a quadratic equation, and we studied all about how those graphs change with changes in equations and all of that kind of thing. Well, we're taking a completely different approach here. The figure is the same, but the equations will look quite a bit different, and our definition for parabola is pretty different as well. We're thinking in terms of distance now, and all of our definitions have to do with distance. And the definition for parabola goes like this. Suppose we start with a point and a line. Now, the point is not on the line. The line is called a directrix, and the point is called a focus. And the parabola is all the points in the plane that are the same distance from the focus and the directrix. That is, we have a point right here midway, you see, between these two. And we have another point, like this distance and that distance are the same. We have another point over here, such that this distance and that distance are the same. We have another point out here somewhere where this distance and that distance are the same. And all such points compose our parabolic curve. So the parabola then would have this kind of shape. And it's the shape of parabolic curves from before. There's no surprise about the shape of it. The surprise is the introduction of focus and directrix. Now, the point right in between the focus and directrix, this point, which is the lowest point on the parabolic curve as I've drawn it here, it might be the highest point if I drew it like this, but it's called the vertex, as we have talked about in the past. We could also talk about a line of symmetry here. If we drew an imaginary line right down the middle of it sort of here, a line containing the focus and the vertex and perpendicular to the directrix, then we would have a line of symmetry, and sometimes this is called the axis or the axis of symmetry. To begin our study, we're going to think about situating this parabolic curve on a coordinate plane in a particular way. We're going to think about the vertex as being located at the origin. So we'll have a configuration like this. Now, we're structuring it this way just to introduce the equation associated with this parabolic curve. And it's a really strange looking equation. It goes like this. Now, when the parabolic curve opens up or down, the equation associated with it looks like this. It's x squared equals 4py. And the reason for having the 4 in here is to allow us to identify the distance between the vertex and the focus. And you know, if we have the distance between the vertex and the focus, we automatically have the distance between the vertex and the directrix, because the directrix is just the same distance on the other side of the vertex from the focus. All right, now, it's the p-value that is the distance from vertex to focus, and it's a directed distance. That is, this p-value, it can be positive or negative. Usually we just assign positive numbers to distances, but now we're going to call this a directed distance because it's a distance that has direction associated with it for the value of p. If p is positive, then the direction is up, and negative, the direction is down, as we'll see in just a few minutes. Okay, so the 4 is in here just to accommodate this idea of identifying the value for p. Now notice, x squared equals 4py. The x squared is isolated on one side of the equation. Now in this study, we're not restricted to the idea of function. You know, we can have relationships between variables that are not function relationships. When we study the circle, for example, it fails the vertical line test, so certainly we're not talking about a function. But in this study as well, we're not restricted to the function idea, so we can have parabolic curves that open to the side like this. Now, here's our focus, here's the vertex, and here's the directrix. And the equation associated with this is y squared equals 4px. Now, notice just the swap of the role of x and y here when the graph kind of opens to the side. I want you to also notice that the parabolic curve tends to wrap around the focus. So it wraps around the focus in this direction. If the focus was over here, then the curve would look like this. And when we're talking up or down, if the focus is above the vertex, then the parabolic curve opens upward like this. And then if the focus were down here, it would open downward. All right, let's see how we would deal with the equations. Suppose we want to construct the graph associated with this equation, which is the equation for a parabola. Now you recognize the equation for a parabola because we have a second degree variable. One of the variables is second degree and the other is first degree. As we continue our study here, it's going to be increasingly important for us to be able to recognize what kind of figure we're dealing with early on in the problem. And that's the way we recognize parabolas. So we have a parabolic curve, and the prevailing characteristic for the structure of our equation, and this is the equation of a parabola whose vertex is at the origin, is what we're really dealing with right now. The prevailing characteristic is that the variable squared is isolated on one side of the equation, and so we'll manipulate the equation to that form. Well, the standard form also calls for us to have a factor of 4, a distinguishable factor of 4. And so what we're going to do is force the factorization of 4 out of the 10. You see, we're going to just snag 4 out of the 10, whether it wants to come out of there or not, whether there's a 4 factor in there or not. And we do that like this. We can say, okay, 4 times what will give 10? Or we might say 4 times 10/4. You see, is equal to 10. And so I'll put 10/4 here, and now I'll simplify that. But that's the technique we use to force that factorization. This is 5/2. Now we identify p as being this 5/2 or 2 1/2. Now that gives us information about distance from vertex to focus, and so we can structure our graph. And it's just a sketch, but here's how we make the sketch. Now at this point you may be thinking, wow, wait a second, we have parabolas that open to the side and parabolas that open up or down. How do we know what kind of parabola we have? Well, that's an interesting question. We have to know which way we go from this origin. We know the vertex is at the origin, and we know that the p-value is positive. It's 2.5. So we're going to go in a positive direction. But do we go along the x-axis a positive distance of 2.5, or do we go along the y-axis a positive distance of 2.5? Well, there are a few ways to be able to tell, but here's a pretty good way. If you have a second degree x and a first degree y, then it implies that one value of y will produce two values for x. So one value for y, let's say that one, will produce two values for x. And then because of that, we have this opening either up or down. Now with a p-value that's 2.5, it's positive, we know that the parabolic curve is going to open upward, because once we find that, see here's 3, so 2.5 would be right here. There's the focus. The curve tends to wrap around that focus point, so the curve then would look like this. And the directrix would be the same distance on the other side of the vertex. So there's the position of the directrix. Now we're just going to be sketching graphs here. You know, we were very careful about sketching graphs very accurately when we studied parabolas before, when they emerged from quadratic equations. We wanted a precise graph. We used the calculator on them and all of that kind of thing. And we could do that here too. In fact, we could make a table of values and plot a bunch of points and discover exactly the behavior of the graph. But really, our study is more concentrated on the manipulation of the equations in a certain form in order to discover the structure of the graph, and not so much exactly how abruptly the curve will occur on the coordinate plane. I will tell you this, though, that as this focus point moves away from the vertex, the parabolic curve tends to sort of lay down. It tends to be more gentle. And as this point gets closer to the vertex, it tends to have a more abrupt kind of graph. Okay, here's another one. Now notice y squared plus 5x is 0. And once again, we see that we have a second degree y, first degree x. So one variable second degree, the other variable first degree. That means that we have a parabolic curve. The way that we deal with it is to isolate the variable squared on one side of the equal sign. Now I've done that here by subtracting 5x on both sides. Now the technique is to force the factorization of the 4. So we go through that thought process like we did before, that 4 times what is negative 5, you see? And you can always identify it by just writing this. Negative 5 over 4, you see, because those would cancel and we would have negative 5. Now simplify this. Well, it's pretty easy to simplify. It's quite simply negative 5/4, which is negative 1 1/4. Now, how are we situated on the coordinate plane for graphing purposes? Well, we have a first degree x and a second degree y. That means that one value of x will cause us to have two values for y. So one value for x, say out here, gives us two values for y as points on the graph. That gives us a curve that opens to the side. Now, I don't want to imply that they all open to the right, because certainly they don't. It could be opening to the left. The x we chose could have been here, and the y is like this. But it's right or left as opposed to up or down. All right, now we look at the value of p to decide the position of the focus. Now, our vertex is here at the origin. Our p-value is negative, so that's the negative direction, left or right, 1 1/4. Let's call this 1 and this 2, so 1 1/4 would be about right here. So the opening then, which tends to wrap around the focus point, looks like this. And the directrix is the same distance on the other side, so it would look like that. Now, in this study, as we have seen a few times in the past, that from a from a teaching standpoint, there are sort of two directions for this study. One direction is where we take an equation and produce a graph, and the other direction is where we take information about a graph and produce an equation. And this next problem is like that. Suppose we want to write an equation of the parabola with vertex at the origin and focus at 2, 0. You see, so with this information, we're going to produce the equation. Now, you begin maybe by just sketching the graph. If we've got a coordinate plane and we know that the vertex is at the origin and we have a focus at 2, 0, then we know an awful lot about the nature of this of the graph. We know that the graph tends to wrap around the focus, so we know we have a parabolic curve that opens to the side and it's opening to the right, and we know that this distance is the p-value, so p is equal to 2, and it's a directed distance, so it's positive 2. We know that the directrix is on the other side. It's over here, a distance of 2. It's not really important to our problem, but we could complete the graph like that. Now we're ready to structure our equation. Now here's what we're noticing. We're noticing that one value of x, or any of the x values along here, are producing two values for y. So we have a y squared situation. So the nature of the equation is y squared equals 4px. Now we've identified the value of p, so y squared equals 4 times 2x, or y squared is 8x for our equation. We could put this in a different form. We could kick the 8x to the other side if we want to and write it as y squared minus 8x equals 0, but I think this is appropriate as a simplified form for the equation corresponding with this information. Now we're going to talk about the equation of the parabola when the vertex is not located at the origin. But it turns out it's pretty easy because we're going to use the same technique that we used with circles. You may recall that when the center of the circle was at the origin, the equation was x squared plus y squared equals r squared. And the center was at the origin. The radius, of course, is r. Now, when we move the circle's center away from the origin, we introduce the idea of an hk. H and k are the hk represent the coordinates of the center, and in the equation we find them in binomials that are squared. So it's x minus h squared plus y minus k squared equals r squared, and the center is at h and k. An important characteristic here to notice is that h and k are numbers that follow minus signs for the identity purpose for the h and the k. Okay, so that's the idea with the circle, and it's the same idea with the parabola. We start with the notion that we have an equation associated with a parabolic curve whose vertex is at the origin. Now, when that vertex moves away from the origin, we just introduce the idea of an h and a k. The h is associated with x and the k associated with y, and we make a couple of binomials here. So as the vertex moves away from the origin like this, we have an x minus h squared and then 4p times y minus k. The vertex is at h and k, and the focus is at h and then k plus p. And let's see why. You recall now that p is the distance from the vertex to the focus. So if we're talking about the coordinates for that focus point, then it would be the same horizontal component you see for the vertex. It would be the h, and then it would be this distance plus p. So it would be k plus p, you see. Now, I don't think it's worthwhile to memorize this. As a matter of fact, I don't think it's worthwhile to memorize this. I think it's worthwhile to remember that and then extend the idea of this into that idea. You see, and it cuts down on the things that we have to sort of recall by rote memory. We just memorize, I guess, the idea of this x squared is 4py. And then we just introduce the notion of h and k. And by doing that, by going through a little thought process like that, we can almost generate our own equations. For example, if we're thinking about a parabolic curve that opens to the side, then rather than try to just outright remember the equation associated with this, we can generate it ourselves like this. We can think, okay, we have a parabola that opens to the side. It means that one value of x is generating two values for y. That means that the y is squared. So if this parabolic curve were located at the origin, that is, if the vertex were at the origin, we would have a y squared equals 4px. Okay, so that's the basis upon which we're working. And now, because we're justifying the parabolic curve away from the origin, we introduce the idea of h and k. And the h is associated with x and the k is associated with y. So this becomes then y minus k squared equals 4p x minus h. You see, so now here's the equation associated with that one. We could talk again about the coordinates for vertex and the coordinates for focus. Of course, the vertex we know is at hk. And we could generate some kind of relationship for focus like this. We could say, well, let's see now. The focus is at, from here we go a horizontal distance which is equivalent to the h and then plus p. So, oh yes, it's h plus p. And then the vertical distance is the same as the vertical distance for the vertex. So it would be k. Consider this problem. Suppose we want to generate the equation associated with this information. We have a vertex at 3, 2, a focus at 1, 2. That's all we know about the problem, but we want to generate the formula or the equation associated with this. We begin by just sketching a little graph. So we think like this. Okay, we've got a vertex at 3, 2. We have a focus at 1, 2. All right, vertex, focus. We know that the curve tends to wrap around the focus. If that's the focus and that's the vertex, then we have this kind of behavior for the parabolic curve. We know that the directrix is out here, but we don't need that information in order to construct the equation. All right, now we just kind of start this thought process. It's the notion that, let's see, we have 1x generating 2y's. So we have the notion of y squared equals 4px. All right, but we're not located with our vertex at the origin, so we introduce the idea of h and k. H associated with x, k associated with y. So we have the y minus k squared equals 4p x minus h. And now, with the information that we have here, it's pretty easy because we just identify, let's see, the coordinates of our vertex were 3, 2. So h is 3 and k is 2. So k is 2. Now notice that the k is following a minus sign here, as we would expect. And then we have 4 times the p value. Let's see, distance from vertex to focus, from here to there. Now we're talking horizontally, and so from here to there it's a directed distance, so it's negative 1, 2. So this is negative 2, and then this is x minus the h value is 3. And we would probably just multiply these and clean up a little bit. We could actually expand it a great deal, but if we want to leave this in a pretty much standard form, then we would probably write it as negative 8 times x minus 3, like this on the right side. In this next problem, we start with the idea of an equation. And let's say we want to construct the graph. And let's also say that we want to generate the coordinates for the focus. Okay, so we would begin like this. We would think, well, I know because of this binomial squared and this binomial involving x that the vertex is not located at the origin. I know that the vertex is at hk, and let's see, h follows the x and k follows the y, and they each follow minus signs. So the vertex is at 5, and we think of this as minus negative 1/2. So negative 1/2 for the k value. All right, I know that much. But wait a second, I need the p value. Oh, it's found right in here. So we need to use a step to identify the value of p, and we do that by forcing the factorization of 4. So we think 4 times 2 over 4 Now we see that the p-value is 1/2. Okay, so p is 1/2. Now, with that, let's see. Vertex at 5, negative 1/2. 1, 2, 3, 4, 5. This is negative 1, so negative 1/2 puts us right here. All right, now, which way are we opening? There's the vertex, but do we open left, right, up, or down? Well, let's see. The y is squared and x is to the first degree. So 1x generates 2 y's. We're opening to the side. Okay, now do we open this way or do we open that way? The value of p will help us with that. P is 1/2. Aha, that's a positive 1/2. So from here, horizontally, positive 1/2, we go over to this point. And the parabolic curve tends to wrap around that point. And the vertex and focus are pretty close here, so I know that the parabolic curve is going to look a little thin. So it's going to look something like this. And now we can identify the coordinates of the focus pretty easily. Let's see, we go over 5.5 and then down 1/2. So the focus has coordinates 5.5, negative 1/2. And what about the directrix? You know, the directrix is the same distance on the other side, and sometimes you might be called upon to write the equation for the directrix. And let's see, it's a vertical line, and vertical lines are x lines, and they are x lines at a particular distance from the y-axis, and that distance is 1, 2, 3, 4.5. So this line is x equals 4.5 as the equation for the directrix. Well, in this next one, we have an equation that is in general form. It's kind of in an expanded form. We don't know anything about the graph by looking at this equation. So we have to manipulate it into standard form in order to read the information we need for graphing purposes. Now, to do that, here's what we first think. We see that we have y squared and x is to the first degree. Now, that tells us we have a parabolic curve, and it tells us about how to situate the terms on one side of the equation or the other. We're going to put the terms involving y on one side of the equation and all the other terms on the other side. Here's what we're thinking. It's y squared plus 6y. Now I'm going to leave a space here, and on the right I'm subtracting 8x on both sides. Whoops, I'm subtracting 8x on both sides, so I'll get negative 8x on the right. And I'm subtracting 25 on both sides, so I'll get this. Now, you're probably anticipating I hope you're anticipating what I'm going to say about this, because we've seen it before. We have to use the technique of completing the square here in order to cause a condition of a binomial squared over here. And as I say, we've seen it before, so we know the technique. And the technique is to identify the constant here that can be associated with these two terms to cause us to have a trinomial square, which factors into a binomial squared. So we are completing the square. We are completing the trinomial square. All right, half of 6 is 3. 3 squared is 9. So we're adding 9 over here, but we're causing an imbalance in the equation. To maintain the balance, we have to add the same amount over here. So we're going to add 9 on the right side. Now back over here, we factor, and as expected, we get y plus 3 squared. On the right, well, let's see. We're collecting and so forth, and we get negative 8x, and then negative 25 plus 9, that's negative 16. All right, now what? Well, gee, we have a couple of things to do over here. And one thing we ought to realize, and we need to realize in beginning the manipulation on the right side, is that the form that we're trying to take is this. It's y minus k squared equals 4p times x minus h. And one thing we know is that we're going to have to force the factorization of 4. But there's a subtle situation here we have to deal with, and that is that in this parenthesis, the understood coefficient of x is 1. So before we deal with the 4, we need to deal with that binomial involving a coefficient of 1. You see, a binomial involving x with a coefficient of 1. So that means we need to factor out this negative 8. You see, before we go looking around for that 4 business. Okay, so here's what we do. We bring down the left side, and we yank this -8 out of these 2 terms. Now, it's convenient here because 8 is a factor of both of the terms, but even if it weren't, we would have to force the factorization of whatever this coefficient turns out to be. So we have -8 times x. Let's see, -8 out of -16, oh, that leaves +2. Now we go about identifying the p-value by forcing the factorization of 4 out of the -8. So 4 times -2 times x plus 2. Now we have all of the ingredients that we need. We know that we have a vertex at hk. Now h follows a minus sign and it's associated with x. So this is x minus -2. So -2 for the h value, and the k is here, minus -3, so -3 for the k value. And we have a p-value of -2. Now let's sketch the graph. Let's come back this way. Let's see, the vertex is at -2, -3. Here. Okay, now how is the graph situated? Well, we will go back over here and we see, oh, second degree y, first degree x. So 1x gives rise to 2 y values. Again, we're opening to the side. Okay, so we're opening to the side. That means that the distance p is taken as a horizontal distance, and that p-value is -2. From here, let's see, the positive direction is that way, negative direction this way, so we go to the left 2. All right, here we go. Now, the graph tends to wrap around the focus from the vertex, and so that graph maybe looks something like this. All right, now, what about the coordinates for our focus? That might be something that we would be after in a problem like this. And let's see, it would be -1, 2, 3, 4, and then down 3. So -4, 3. Now, notice I'm reading this off of the graph. I'm finding the coordinates of the focus from the graph rather than trying to think of some algebraic method for doing this. We could generate an algebraic method easily enough, but it causes us to have something extra to remember. And so just looking at the graph makes it a lot easier.